Next up on our tour of the properties of light, and sometimes sound, is an effect first explained by an Austrian mathematician and physicist, Christian Doppler, in 1842. In a paper entitled On the Coloured Light of Binary Stars and Some Other Stars of the Heavens, Doppler presented his theory that observed frequency of wave depends on both the emitted light and on the relative speed of the source and the observer. But what does this mean? Well, if we switch back to sound waves for a moment, we can use a real-world analogy to explore this. I'm sure many of you have been present as emergency vehicles or a train pass by. When this happens, what do you hear? Well, yes, you hear the siren, but what happens to the siren as an ambulance drives by? Well, if you listen closely, you can hear that the pitch of the siren changes over time. As the ambulance moves towards us, you hear the siren at one pitch, but as it passes by, it seems to drop in pitch. Let's listen to the sound of a passing train to compare the sound of the effect from a different source. There is a clear drop in pitch. But what is the reason for this? Let's take the example of trains and look at this in more detail to explore the physics of the Doppler shift. As the train sets off, we begin to see things change. The sound waves in front of the train begin to bunch up and are pushed together. When the wavefronts of the sound waves are pushed closer together, the wavelength that a stationary person will hear will be smaller. Smaller wavelengths correspond to higher frequencies and higher pitch. When a train or ambulance approaches, you hear a higher pitched sound. Now, if we look at the waves behind the train, we can see that as the vehicle moves forward, the waves appear to be more spread out. This apparent stretch results in longer wavelengths or lower frequencies, which results in a lower pitch. As a train moves past us, the shift raises the pitch as it moves towards us, has no effect as it's next to us, and lowers the pitch as it moves away from us. Curtis has an electronic sound device that emits a sound wave with just one pitch. As he twirls the sound emitter in circles, we can hear the sound waves change in pitch from higher and lower pitches as the emitter moves towards us and away from us. This raising and lowering of pitch is known as the Doppler effect. And as we hinted at earlier, it also applies to light. As light is emitted from a source, the waves being emitted can be squashed or stretched along the direction of motion. So, if a star is moving towards us, the light waves moving ahead of the star can appear to be increased in frequency or decreased in wavelength. This translates as a shift towards the bluer end of the electromagnetic spectrum. Conversely, as a star moves away from us, the waves appear to be stretched, resulting in longer wavelengths and a redder look to the star. For light, the shifts caused by the Doppler effect are known as blue shift and red shift. Although we should note that this is not confined to the visible band of the electromagnetic spectrum. Both X-rays and radio waves can also be blue and red shifted. The colours just speak to the direction of the shift. While stars do not normally race around in cars, they are moving around in space. Many stars that are observed in the night sky are actually in binary star systems. In such systems, we see stars in orbit around one another. If we view a pair of stars from the side, it will appear as though one star is moving towards us while the other star is moving away from us. This relative motion is detected as blue shifts and red shifts that we detect from these stars. The same is true of galaxies. Spiral galaxies are found spinning and spiraling in space. In fact, our own galaxy, the Milky Way, takes about 240 million years to complete one full rotation. When we look at other galaxies, we can measure the light emitted at various points across the disk to deduce the galaxy's speed of rotation. When measuring light from stars, we see a shift in light towards shorter wavelengths from the side of the galaxy approaching us. It's blue shifted. If we look at the other side of the disk that's moving away from us, we can see a shift of light towards longer wavelengths. So it's red shifted. It's interesting to note that while one of our closest neighbours, M31, or the Andromeda galaxy, is rotating, we also see an overall blue shift of the whole galaxy, implying that M31 is moving towards us. While there are many other examples of the use of redshift and blue shift in astronomy, the most well-known Doppler shift in astronomy triggered the idea of the expanding universe. In the early 1900s, the prevailing theory was that the Milky Way, our own galaxy, was pretty much the extent of the universe. In the early 1920s, an astronomer named Edwin Hubble was working at the Mount Wilson Observatory in the USA. He was making measurements of the distances of various nebulae, only to find that some, including what was then known as the Andromeda nebulae, were far too distant to be part of our own galaxy. Instead, these objects must be galaxies in their own right. This meant that the Andromeda nebulae became known as the Andromeda Galaxy, the one just mentioned a few moments ago. Although the idea of multiple galaxies had been proposed as early as the mid-1700s, it's strange to think that the concept of galaxies is so new. This idea was only conclusively proven about 100 years ago. In 1929, Hubble continued these observations and found a relationship between the distance and the redshift of galaxies. Hubble found that galaxies that are outside of our local group of galaxies have light that is redshifted. Not only is the light redshifted, he also saw that the further away the galaxy is from us, the larger the change in wavelength, or the larger the redshift. If the change in wavelength is interpreted as a Doppler shift due to the motion, then Hubble's observations suggest that galaxies appear to move away from us. Galaxies that are further away from us are moving away from us at a faster speed. The modern interpretation of Hubble's observations is that the universe is expanding, which it makes it look like galaxies are moving away from us. The description of the expansion of the universe is called the Big Bang theory. The Big Bang explains the evolution of the universe after its beginning, 13.82 billion years later, we find ourselves here on the Earth learning about black holes. Speaking of which, if we are wanting to understand black holes, we need to understand something about gravity. For that, let's start with the simplest version, Newtonian gravity.